Today you will start a module on polymers. So, what are polymers? Polymers are very long molecules with many repeating units, often described as chains. The word polymers comes from the Greek poly, meaning many, and mers, meaning parts. Polymer, many mers, many parts. To get started thinking about polymer chains, let's first talk about simple hydrocarbon molecules. Methane, the primary component of natural gas, is the most simple hydrocarbon with one carbon atom. Propane, a common heating fuel, has 3 connected carbon atoms. Octane and gasoline has 8 carbon atoms. Vaseline has about 20 carbon atoms per chain, and wax is about 50 carbon atoms per chain. The polymer with the same hydrocarbon structure is called polyethylene. How many repeat units does it take before we call a molecule a polymer? Some say that chains with over 2,000 repeat units behave like polymers. If you make a pot bead chain with 2,000 beads, this is how long that chain is. Really, really long! When thinking about polyethylene, each monomer unit is 2 carbon atoms. So for a polyethylene chain to behave like a polymer, it must be at least 2 times 2,000 or 4,000 carbon atoms long. The molecular mass of each polyethylene monomer unit is 26 grams per mole. So a polyethylene chain with 2,000 monomer units has the molecular mass of 52,000 grams per mole. The polyethylene chains in common milk jugs have molecular masses of 200,000 to 500,000 grams per mole. And very, very long chains of polyethylene with molecular weights over 3 million are used to make body armor. Where else do we find polymers? You are familiar with many biological polymers, such as proteins, DNA, and carbohydrates, like cellulose or cotton. You are also familiar with many synthetic polymers, commonly known as plastics. Plastics that may come to mind first include polyethylene plastic bags and milk jugs, polyethylene terephthalate soda bottles, polystyrene cups, and expanded polystyrene foam. These plastics share some common physical properties. They are all electrically insulating, thermally insulating, and insoluble in water. Plastics are also commonly found in other places, such as tires, automotive bodies, home siding, contact lenses, diapers, and paint. And scientists have engineered polymers to have special properties that you might not associate with plastics. Now, we have made polymers that conduct electricity, polymers that can effectively transfer heat, and polymers that are magnetic. Polymer research scientists and engineers are still designing and making new types of functional polymers. My research group studies how to conduct ions, charged atoms, through plastics for use in batteries. So what determines the properties of a polymer? Polymer material properties are determined by both chemistry and physics, by the molecular identity of the monomer units and how individual units and the entire chains are structured and interact. Linear homopolymers are long chains with a single type of repeating unit. The chains get entangled with one another and are sometimes described as looking like mixed up spaghetti. The entanglements between the polymer chains are what gives rise to some of the interesting mechanical properties of plastics, like flexibility and stretchiness. Polymers can also be branched, like the low-density polyethylene used to make plastic bags, or cross-linked into a network, like superabsorbent polymers used in diapers. Polymers are also made with repeating units of different chemistries. These are called copolymers. The different chemistry monomers can be randomly arranged or segregated into blocks, and the copolymers can be made in all of the different chain morphologies, like linear, branched, and cross-linked. All of these possibilities make plastics nearly infinitely tunable materials. Finally, how are polymers made? Linear homopolymers can be synthesized by 2 main routes. With addition polymerization, all of the monomers can be the same. After an initiation step, some of these monomers become reactive and link with their neighbor. The new monomer just added is now reactive and links with another neighbor. This happens and the chains grow until there is no remaining monomers to react. The second technique is condensation polymerization. Here, there are two different types of monomers, some acidic and some basic. The acidic monomers can only react with basic monomers and vice versa. When the acidic and basic monomers join, they produce or condense out a small molecule byproduct such as water or HCl. The single monomers join to make pairs, the pairs join to make chains of 4, these join to make chains of 8, and so on. Today, you will make nylon by an interfacial condensation polymerization. The basic monomer is soluble in water, and the acidic monomer is soluble in hexane. Remember, oil and water don't mix. The solution of the acidic monomer in hexane will sit on top of the aqueous solution, and nylon will form at the interface. Have fun!